Well, good evening, class. It's early evening now. It's 5 o'clock. This day sure has flown by. Real quick here, I just wanted to touch base with everyone, and uh, there's been some students that have reached out to me and let me know that there's still some things that could be clarified a bit regarding the Skew-t log P diagram. So I'm very happy to be able to be helpful this afternoon, this evening regarding that. So we'll go ahead and just take a look. I was asked if I actually had a copy of the laminated Skew-t that you guys are using. Some of you are using. I know some of you have purchased the Skew-t diagram, the laminated version that Tim Vasquez has on his website. And there's also, I think, another one available out there somewhere. But the actual one that's produced by Mississippi State University, I know that the bookstore ran out of those there for a while, so those were not available for a period of time. I'm not sure if they're back in stock yet. I haven't called up there in a while to see, but they were out of stock for a period, and I know that many folks went and purchased them off Tim Vasquez's website. There, I think it's weathergraphics.com. If you're interested. But the one that's from the bookstore looks a lot like this one. I've seen it, I've laid my hands on it, but I've never purchased one. And so this is one that was produced, I think, by Noah many years ago, probably back in the 70s. But we'll just zoom on in here and I'll kind of clarify the lines for you, make it a little bit easier to understand. I know the Skew-t diagram is a concept that it just takes time. It's one of the most difficult concepts in meteorology, frankly. It took me a while to do it, as I told you last time, to be able to understand it well. About 10 years ago when I had my first thermodynamics course, a lot like this one. Okay, so we'll start off by looking here at the bottom. You can see the mixing ratio as in blue. Remember, with some of the diagrams I've been showing on the quizzes and the exams and stuff have been in purple. And I had one student that actually made a very good comment about it's probably best to learn how to read it by judging the slope of the lines, the character, the geometric proximity of the lines to each other and to the diagram as a whole. So for instance, the mixing ratio lines, they're going to slope up and to the right, but they're at a steeper incline. Their inclination is greater. They're at a steeper angle to the surface than the temperature lines. See, the temperature skews, they go up and to the right as well. And those are, of course, these dark brown lines here. I'll zoom in a bit more for you. But the mixing ratio lines, here's the temperature lines here. There's 10. There's 5, 0, etc. All the way across. Excuse me. That's that's 10. Looks like 0, 10. So it is confusing because each one of these little lines is 1. So 11, 12, 13, 14, 15, 16, 17, 18, 19, and then you get to 20. And so that does get confusing. I'm looking at it here just to make sure I'm telling you correctly. Excuse me. No, that's we're all the way to the left. So we need to move right. Yeah, that was right. So 10 through 20, 20 through 30, 30, 40 isotherms. Okay? And then mixing ratios, they're the blue lines because they're the steeper slope that runs from lower left to upper right. Okay, so whether this line is blue or purple or red or teal, yellow, whatever, as long as it runs from lower left to upper right and is at pretty steep angle here, steeper than the temperature skews, which for instance, we'll just take the 20 isotherm, run it up and to the right. 20 is right here. Run it up and to the right. This 20, see the numbers are oriented. It's taken me a minute here. The numbers are oriented parallel to whatever indice or parameter it is. So this is the 20-degree unsaturated adiabat. See that? There's the 30 dry adiabat right there, 40 on up. So the numbering is parallel to whatever parameter we're referring to. Okay, so there's the 20-degree isotherm. There is the 25-degree isotherm, 30. See that? There's the 30 isotherm. And then the dry adiabats, 30, 20, 10, yada, yada. Okay? And so then something else to consider is the moist adiabats. Those are these green lines right here. And they're labeled here. I'm not sure if the MSU produced Skew-t diagram is done the same way, but that's what these are. These are the moist or saturated adiabats, okay? 26, 28, 30, 32, etc. Okay, so some of these black lines, like these lines here, these vertical dotted lines, don't worry about that. There is some extraneous stuff on here, stuff you won't need for this class. So just focus on the bulk of the things we've talked about. And let me go down here. I've actually produced a chart that may help. I think I've shown this before. Let me pull it up. It's here we go. Okay, so this chart, I believe, is just this one zoomed in to a section there of the lower portion, the bottom. There we go. Okay, so as you can see, the mixing ratios in blue this time. Isobars are going to be in the brown. Everything other than the mixing ratios and the saturated mixing ratios are going to be in brown on this particular diagram. So there's a little explanation for you there. Down here at the bottom, I tell what everything is. So let me try to get it all in one frame for you. There we go. That ought to help. Okay, so there's the whole thing in one frame, and you can see the legend and everything down there at the bottom. That'll help you out in being able to decipher what's what. Okay, and so the other thing I'll do is I'll go down one more slide. This is something else, another document I prepared a while ago. And I'll zoom in. This is a little screenshot from the Sharpeye program. I don't know if any of you have, I know most of you have used soundings from the Sharpeye program. It's what's generated like with the point and click sounding system on like Pivotal Weather or COD, College of DuPage, and a lot of those point and click model sites that are very useful. Will generate a sounding a lot like this one, minus the annotation. A lot of this annotation I put on there, but it'll generate a Sharpeye sounding for you if you'll click on the geographical location that you wish to get this sounding for. So there's a little bit of explanation there, a little bit more detail on what's what. We'll just scroll through this here. You can see the area of Cape, which lies between, as we've learned, we'll learn more about this. I know that Professor Habe on the lectures has touched on this. Jeff Habe's touched on this a little bit in the lectures, the video lectures. But it's the area that lies in between the parcel temperature, which is this line right here, right north of the LFC, level of free convection. And then it bombs away all the way up to the equilibrium level. And then that's where the area of Cape stops. Here's the temperature profile in red, dew point or moisture profile in green, lime green there, the winds. This will help maybe clarify some other things. The mixing ratios on this particular diagram are green, and you can see them down here, saturated mixing ratios in green there. There's some details of things on here we haven't talked about. Of course, we've talked about the temperature inversion. The LCL, of course, the lifted condensation level. The LFC is just the point, the lowest point in the Cape profile. So that's right here. We'll get to that more here in coming weeks. The wet bulb zero, your wet bulb temperature profile. So the wet bulb temperature, the wet bulb zero line is going to be right here. That's where the wet bulb line crosses the 0-degree isotherm. So that's one of the questions on your quiz 7. So that'll help out a little bit with that. And you find the 0-degree isotherm, which is this blue line right here. Remember, the mixing ratio lines are steeper than the isotherms or temperature lines. So that'll help with that. And there's your wet bulb temperature. So where is your wet bulb temperature? At what pressure does your wet bulb temperature cross the 0-degree isotherm? That would be right here, or roughly about 650, 675 millibars, right in through here. Okay? One interesting thing I'll throw out there, I know we haven't talked a lot about CAPE yet, but for some of you who may know kind of what CAPE is, I'm sure most of you do, working with severe weather and stuff over the years. The highest point that a thunderstorm will get is once a parcel has risen through the CAPE profile, okay, and you get to the equilibrium level and the atmosphere is no longer buoyant, it's statically stable, or partial stable, excuse me. Static stability starts here, right? It just depends on the lapse rate itself. But the partial stability starts here, where the partial temperature crosses to the left of the temperature profile, which occurs at the equilibrium level here. Okay? The max parcel level, the MPL, is when this area bound by the temperature profile and the parcel temperature north of the equilibrium level, when that area here in light gray, when this area matches this area within the CAPE profile, that is as high up as a thunderstorm can get, north of the equilibrium level. Because remember, above the equilibrium level, the cloud's not just going to all of a sudden stop. It's going to have kinetic motion. It's just going to keep on rising until those two areas are equal there, so to say, on a graph. That's when the MPL is reached. Okay, so I sure hope this has helped everyone. Between these three diagrams here going over things. If you have further questions, do let me know. I'd be happy to go over it again or to do what I need to do to help everyone succeed. And I will let you know, I'm planning on giving everyone a third chance on the midterm exam. That'll be coming up. I'll go ahead and extend that now. So this evening through, and I think the midterm is scheduled to be due in 2 days at 12 p.m., so on the 23rd at 12 p.m., I'll extend that through Friday. Okay, so the midterm will now be due October, let me get it right, 25, October 25th at 12 noon will be the midterms deadline, and we'll make that happen. You guys are doing great. Just keep it to the grindstone there, and don't forget, this is the hardest part of the class, this portion, and then running through about mid-November. That will be when we go over hodographs, Skew-t diagrams. The Skew-t log P diagram and hodographs complement each other when forecasting severe convective weather. So we'll need to cover hodographs as well. And then we'll kind of culminate everything, and you'll learn how to produce better severe weather forecasts. And we'll go a little bit into tropical weather. Not much, just a little bit. I think we barely touched that, but that is in this class as well. But mostly from here on out, folks, it's severe weather forecasting, and I want to make it fun. I want you guys to enjoy it, and we're going to wrap up the semester real quick here. I'm sure a lot of you have thought about that, but if you haven't, that's there too. So this thing's going to wrap up really quick. Okay, well, you guys have a great day, and take care, and I'm here if you need me. Have a great day. Bye-bye.